Thank you all for subscribing to this sensory data analysis webinar. So this is part one. We'll be seeing how to evaluate differences between products. The webinar will be illustrated with the XLSTAT software. So some of you have already used the software. Otherwise, it will be a good opportunity to discover it today. So there will be another webinar, so part two, on Thursday, which is also about sensory data analysis. We'll be talking about another topic, how to link affective data to sensory attributes. So the sensory data analysis methods are there's a very rich ecosystem around this. So unfortunately, we won't be able to cover everything available in this world, and especially in XLSTAT. So if you want to go further, if you'd like to go further, don't hesitate to contact us and to request maybe some further training, which will be more tailored to your specific needs, or to do some more research on your side. So my name is Jean-Paul Maalouf. I'm a statistical consultant at XLSTAT. You should know that there are handouts and data you can download for this webinar. So the presentation handouts are available somewhere on the webinar platform. That there must be a download button somewhere. You may submit all the questions you have on the chatting pop-up window. I'll be answering as many questions as I can at the end of the webinar during the last 5 minutes, maybe during a Q&A session. There will be a recording available of this webinar. It will be available by the end of this month. So you will receive a link to the recording. So if you have any colleagues who were interested by the webinar and weren't able to attend today, you will be able to share the recording with them without any problem. Okay. So sensory data analysis part one. Here's the outline of this webinar. I'll first start with a few words about XLSTAT. I'll say who we are. Then we'll be stating a few definitions. And I will be talking then about sensory experiments and some popular sensory experiments. We'll be talking about different experiments that allow to evaluate the differences globally among products without necessarily getting into the details of the sensory characterization of each and every product. So this webinar will be really focused on this kind of experiments today. So among these experiments, we'll be investigating a few discrimination tests, such as the triangle test and 2AFC. We'll be also talking about projective mapping and mapping, and which will be exploring through the STATIS data analysis method. And at last, we'll be talking about sensory product characterization, which is used to describe specifically, attribute per attribute, a series of products. So who are we? XLSTAT is a statistical software that works as an add-on to Microsoft Excel, PC, and Mac. It's also available for Excel 365 and Google Sheets, so you can also use it on the cloud. So it's being developed on the cloud today. XLSTAT is developed by the Addinsoft company. It has more than 220 statistical features, more than 150K users worldwide, more than 25 employees at your service, 300K monthly visits on the website. The software is available in 7 languages, and we have offices in 3 different time zones, so America, Europe, and Japan. And there are 10K monthly downloads of the software. So XLSTAT is developed by the Addinsoft company, which is hosted inside the Data Factory. The Data Factory is a private lab dedicated to data science, which is located in Bordeaux in France. It also hosts 4 other expert companies dedicated to data science once again. There are more than 45 people working at the Data Factory, and it organizes more than 25 workshops, events, and trainings around data every year. So it's very active. XLSTAT is available in 8 different solutions to meet your specific needs. So first, there are 3 generalist solutions: Basic, Basic Plus, and Premium. So Basic has the most basic statistical features, such as ANOVA, PCA, or regression, or basic tests. Basic Plus adds machine learning to all the basic features, and Premium holds the complete 220 XLSTAT features. So this is the most complete solution developed by XLSTAT. Between Basic Plus and Premium, you will find many intermediate solutions such as sensory, life sciences, marketing, forecasting, and quality. These solutions are field specific. So today we'll be focusing on the sensory solutions. You should know that each feature in XLSTAT has a dedicated tutorial available online with an associated downloadable dataset. So in each tutorial, you will have an overview on how the method works and how to configure it in XLSTAT and how to interpret the results. So there are many learning resources around features on the XLSTAT website. There also is a YouTube channel developed by the XLSTAT team. It shows different short videos. Each video is dedicated to a specific feature, once again explained briefly and intuitively, and with an illustration using XLSTAT. A few months ago, we recorded or we broadcast several webinars on general statistics, like for data description, data exploration and clustering, statistical testing, statistical modeling, and ANOVA and machine learning. The recordings are available online. You simply need to click on this page on your PDF and you'll access the page if you want to view those webinars again or to discover them. So it's a very good introduction to statistics. So let me just show you how the page looks like. There it is. So you have the different webinars available here with the video and the presentation materials that you can download and manipulate. So here are a few definitions. What is sensory analysis? Sensory analysis is the science that applies the principle of design of experiments and statistics on human senses, which are smell, taste, sight, touch, and hearing, for the purpose of evaluating and optimizing consumer products. Of course, sensory analysis is widely used in the food industry, for instance, to optimize the taste of food. And it's also used in cosmetics to optimize the smell or the touch of different cosmetics products. But it's also used in many, many other consumer goods. For instance, in the car industry, sensory analysis can be used to optimize the sound of the car door closing to make it feel more secure, for instance. Or it can be used in sportswear industry to optimize the softness of a shoe, for instance, for it to feel more comfortable. So notice that in all of these examples, I've mentioned two categories of variables. So the category of a category of variable which refers more to the senses. So how a food tastes, is it acid, is it salty? How a shoe feels like, is it soft? Or how a car sounds, like loud or feels like other kinds of sounds. And on the other hand, we have variables which are more linked to affective feelings, such as feeling more secure or feeling more comfortable or liking more a kind of product. So we will see, especially during the next session, some tools, some sensory analysis tools that allow us to mix these two kinds of variables, so sensory variables with affective variables, in the purpose of optimizing the sensory characteristics to maximize liking and affective variables. So here are a few words I will be using a lot during those two sessions. What is a product? A product is an object characterized by sensory or affective properties. What is a panelist or a judge or an assessor? It's a person evaluating products. A panel is a group of panelists, group of judges. And panelists can be either trained experts, for instance, experts who are trained to tasting and grading wines or sensory characteristics of wines, or they can also be consumers recruited on the market who are untrained. What is a sensory attribute? It's a sensory descriptor of a set of products. For instance, in food, acid and salty and crunchy are sensory attributes that are linked to taste. In other industries, you can have vibrant or small or loud, which are other sensory attributes. Affective testing is measuring the degree of acceptance or liking or any other emotion triggered by a product. So it can be preference, liking, and other emotions. And as I told you, there are methods which allow linking these measurements to these. Okay. Now, how do we measure sensory attributes, or do we measure affective data? So very often these variables are measured on quantitative or ordinal scales. So here's an example of a popular scale used in this case. The 7-point Likert scale. For instance, we may ask in sensory surveys, to what extent do you perceive sweetness in this yogurt? And we submit a scale to the panelists that goes from not sweet at all to extremely sweet, with 7 possible points along the scale. And the assessor simply needs to choose one of the points. Otherwise, you can have other questions which are more effective. So how much do you like this product? Also can use a 7-point Likert scale that goes from not at all to very much. So there are several types of sensory experiments, and the choosing the right type depends, of course, on your question and on the type of data you have. So among the common families of sensory experiments, I will present 3 families today. The difference experiments. The purpose of these experiments is to evaluate distances among products without really getting into the details of sensory characterization. In food products, for instance, here in this case, we won't be getting into the details of measuring how salty the product is, or how acid the product is, or how sweet the product is. Here are examples of questions we may ask in this context. Does changing the recipe of a product induce a difference in its general perception? In this case, you can use discrimination tests. Or is it possible to map products according to their global differences? In this case, you can use projective mapping and mapping, or free sorting experiments. Of course, there are many available methods out there, and many of which are available in XLSTAT. So this is a guide here you can click on to access a comparison of all of the methods available in XLSTAT. I think this guide includes like 25 different methods which are compared to one another, and you can use this guide to choose the right method you need for your specific purposes. Okay, so we've seen the first kind of experiments in the sensory data analysis world. Then you have descriptive experiments that go more thoroughly into the details. So here judges evaluate products over several attributes. So we're not judging things over a global scale anymore, and sometimes over several sessions even. So here are a few questions we can answer out of these experiments. Which attributes characterize this product compared to other products? Or also we can ask which sensory attributes are well discriminated by judges across the products. In this case, we can use sensory product characterization to answer this type of questions. Then we can ask other questions also, over which attribute is there a consensus in the panel. In this case, you can use panel analysis, which also uses data from descriptive experiments. Okay, so during this webinar, we'll be seeing many types of difference experiments. We'll be seeing a few discrimination tests, and we'll be seeing projective mapping, so to map or to measure the differences between products on a global scale. And we'll also have a look at sensory product characterization, which will help us get more into the details of which specific attributes characterize this product or this other product. Of course, descriptive experiments are more expensive, more hard to set up as compared to difference experiments. Then just to tell you, this is how a descriptive experiment data looks like. So this is a data example. We are evaluating 6 brands of chocolate drinks over 2 sessions. So here, as you can see, you have a panelist column, session column, a product column, and 1 column per attribute. And these attributes here are assessed on a 9-point Likert scale. So as you can see, you have 1 row per panelist, product, and session. See, this panelist is repeated 6 times over the first session, 1 time per chocolate product. There are 6 products. So this is the third family of sensory experiments I wanted to tell you about. Effective testing. I've already told you what effective testing is. Effective testing is measuring the degree of acceptance, liking, or any other emotion triggered by a product. And these data have different formats, for instance, liking score or choice of this product over the other because we like it more. And here are the questions we may ask out of these experiments. Which product has the highest liking score? Simply like that. Well, with this, we can simply run basic ANOVAs or parametric or non-parametric tests to answer this question. We can also ask, do consumers who like product A tend to also like product B or tend to not like product C? In this case, you can use more multivariate approaches, such as internal preference mapping, which we'll be talking about in the upcoming webinar, so on Thursday. Stay tuned. And lastly, it is possible to combine the sensory descriptive experiments and the affective testing for the purpose of optimizing product sensory attributes to maximize affective variables. So should we increase saltiness in this product to make it more appreciated by consumers? Well, in this case, we can use external preference mapping, metadata analysis, penalty analysis, which will be tackled during the upcoming webinar. So today we'll be focusing simply on measuring the differences between products and not focusing on to what extent do consumers like these products at the affective scale. So I'll be focusing on difference experiments. Here are a few common methods. Sensory discrimination tests. These tests help determining if the sensory difference between only 2 products is detectable. For example, we change the formulation of a product while hoping its perception by the consumer does not change. Okay, so in order to see whether the perception by the consumer changed or not, we can set up a sensory discrimination test. So common discrimination tests include the triangle test, do a trio, 2 out of 5, 2 AFC, 3 AFC, and tetrads. You can click here for details to see how these tests work and what they are used for on this article, on this page. So all of these are available in XLSTAT. In case there are more products to compare, here we are only comparing 2 products. In case you want to compare more products at the global scale, you can also use free sorting experiments or projective mapping or mapping. So how does free sorting experiments work, theoretically? In free sorting, assessors classify a series of products into groups of products they feel are similar. So imagine you have a set of 5 products, could be 5 different wines. These 5 wines are submitted to a panel, a series of judges. The first judge classifies the products or the wines like this. The first judge thinks that the wine number 3 and wine number 5 are similar to one another, so she classifies them into the same group, and 1 and 4 into the same group, and 2 is a bit atypical compared to the other two groups. Judge number 2 does the same, so some kind of classification, and judge number 3 does the same also. Judge number 3 has detected 4 different groups of wine. So here, as you can see, the wine number 3 and number 5 are often classified together, at least for judge 1 and judge 2. Look, you find them here, and you can also find them here. So how can we sort all of these data out to try to see which are the wines which are mostly similar to one another and different from one another? We can use statistical methods such as correspondence analysis or STATIS to draw a map of the distances between the different products. Okay, there's another way to reach this kind of maps. It's by using projective mapping or napping, and this is how it works. Assessors are asked to arrange products on a sheet in a way to place similar products close to one another and dissimilar products far from one another. So here's the sheet for judge number 1. This judge number 1 will taste also the 5 different wines and will place them on the sheets according to their differences. So for instance, judge number 1 will start by placing the 5th wine here and the 3rd wine close by, because judge number 1 thinks the 2 wines are very similar. Then he thought or she thought that product number 1 is different from them, so it was placed a bit far away. And we have another cluster here at the bottom, so P4 and P2, which are close to one another but different from the others. Then judge number 2 does the same, and judge number 3 also. Here, as you can see, we find once again this interesting clustering between P3 and P5, found here, and found here. But there's some kind of a distortion linked to each and every judge. Here they were clustered at the top right part of the map. Here they were clustered at the bottom left part of the map. And here they were clustered once again on top right. But we see here that the wines are more clustered in the center of the sheet. So statistical methods such as STATIS will help eliminate these different distortions proper to each and every judge to produce one synthetic map of all the distances between products. And how does a typical STATIS map look like? Looks like this. So you have a map that looks like a PCA map, and blue dots are the products. So for now, I won't be commenting too much this kind of maps. We'll have another example later on today to see how to interpret. But you should know that products that are close to one another on the map are pretty similar. So for instance, these 2 products are similar, and they are quite dissimilar from these 3 products, which are similar among them. So we have a group of similar products here, and a group of similar products here, and some atypical products which are a bit far away from them. So let us take now several examples and run application XLSTAT. So I will start with a triangle test. The goal is to check if there is a global sensory difference between only 2 products. Here we are investigating 2 products in sensory discrimination tests. So here's how it works. 3 products, including 2 similar products, are presented to each judge or each panelist. And then every judge tries to identify which product is different from the 2 others. So here's how it works. Judge 1 will receive 3 products, one of which is different, but judge number 1 doesn't know which product is different from another. Here we know it because it's colored in green, but judge number 1 doesn't see it. And we ask judge number 1 which product is different from the others, and judge number 1 chooses one solution, gives an answer, and this solution is either a success or a failure. In this case, it's a success. So judge number 1 was able to perceive which product is different from the others. Then we repeat the same for judge number 2 and judge number 3. And at the end, we simply compute the success rate. And if success rate is high, the 2 products are easily discriminated. So if judges tend to succeed in determining which product is different from the 2 others, then the 2 products are easily discriminated. Depending on the question, this can be either good news or bad news. We'll see an example right away. As a lemonade product manufacturer, you modify a part of the production process to make it cheaper, and you want to make sure the taste perception does not change. So the triangle test helps evaluating the sensory difference between the product from the former process and the product from the new one. In this specific case, we really wish or we hope that judges won't be able to discriminate well the two products. So 30 panelists are asked to taste 3 lemonades each, 2 which are similar and 1 which is different. And each panelist must then try to identify which one is different from the other 2. First step, we need to design a sensory discrimination test experiment to ensure an optimal randomization of trials, and then we launch the experiment and analyze the results. So let's see how we do this in XLSTAT. So this is Microsoft Excel with XLSTAT menus incorporated inside as an add-on. So as you can see, you have several statistical methods which are quite basic, so such as PCA, such as modeling data features, or such as correlation tests, parametric and non-parametric tests. Now we'll be focusing on this specific menu, which is part of the sensory solution. I will open it and open the design of sensory discrimination tests because I want to generate a triangle test. So what is my test type? I'm generating a triangle test. So I'm selecting it here. How many assessors or panels do I have? I have 30. Then what are the product labels or product codes? I can ask XLSTAT either to generate random codes or I can select specific codes or specific labels. So these are the labels which will be sticked on the different products when they will be presented to the judges. So each product should have at least 2 labels so that the judge doesn't really recognize the different product with the labels. So the former process product codes are these 2, and for the new process product codes, we have these 2. So we'll select them like this simply. And I click OK. And here we go. I get my sensory design in a new sheet. Okay. What you see here, J1 to J30, are the different judges. So judge number 1 will receive this first sample, then this second sample, then this third sample, and state which one is different from the 2 others. So in this case, the right answer would be this one, because these 2 products correspond to product number 1, and this is the product which is different. So if judge number 1 says UIO here, in this column, you have a plus that appears. That means that it's a success. This judge was able to identify the product which was different from the 2 others. Then here, if, say, this judge said ERT, then the answer is incorrect because here again, the right answer was UIO. So once you fill out all of the data here, you get something that looks like this with all the correct and incorrect answers. So now that we have our answers, we can launch the analysis to see whether there's a significant discrimination between the 2 lemonades. I will go to sensory discrimination tests. I will need to specify which test I'm running. So is it a triangle test, AFC or stuff? I will take triangle test. There are 2 models that allow investigating discrimination tests, the guessing model and the Thurstonnian model. In this first case, I will be using the guessing model, which assumes that judges are either good discriminators or bad discriminators. Then I select my data simply with my mouse by selecting the whole field like this in the data, in this field. Once I'm ready, I click OK, and I get the result in a new Excel spreadsheet. I will comment on the results here in the presentation. So first of all, this is the number of assessors, number of panelists. So this number is easy. Then we have the proportion of correct answers. So how many judges or how many assessors were able to detect the product which was different from the two others. This is the guessing probability. So this is the probability of picking a right answer by chance. Imagine you are a bad panelist at discriminating two products. You are unable to discriminate between the two products, but you pick an answer anyway. You have 1 chance over 3 of picking the right answer by chance because you have 3 possibilities. So this is the guessing probability. This is what this number refers to. Then here you have the proportion of discriminating judges. This proportion is not the same as the proportion of correct answers. Why? Because it's corrected with the non-discriminating judges, or at least the non-discriminating judges who chose the right answer by chance. Okay? So now let's go straight to the point and see what's the outcome of this test. We need to check the p-value and the alpha threshold. Here we see that the p-value is lower than alpha. Consequently, the two products are significantly discriminated. For those of you who are not familiar with how to interpret a p-value, here's the easy version of the definition of the p-value, but which is not the really right version of its definition. The lower the p-value, the more significant the difference is. And the p-value is bounded between 0 and 1. And if the p-value is low enough to be lower than risk threshold alpha, then you can state that there is a significant difference between the two products. So the two products are significantly well discriminated. And this is bad news for us. So the two lemonades are significantly discriminated. We should review our new production process so that we erase this difference in perception. I've added in the following slide the right definition of the p-value in this case. So I won't be commenting on this, but just for those of you who are interested in the real definition of the p-value, there it is. I'd let you meditate on this on your own. Okay, so now that we've investigated the triangle test, let us check another discrimination test, which is 2AFC. 2AFC, or two alternative forced choice. So the goal is, among two products, identify which one has a specific feature. For instance, which one is more acid, which one is sweeter, and stuff like that. So can you see the difference in the purposes, at least, between triangle test and 2AFC? In triangle test, usually we try to see whether two products are globally different, whereas in the 2AFC test, we focus on a specific feature. So we try to ask the judges, which product do you think is more acid or sweeter or softer? And here's how it works. The two products are presented to each judge, and judges try to identify simply the product with the feature. So judge one gets the two products, and we ask him which product is the sweetest. He gives an answer, the green product, and we know that the green product is the right answer, so this would be a success. And judge number two failed, and so on. So we ask the same question to different judges, and then we measure the success rate. If it's high, the feature is easily detected in the target product, and if it's low, it is not. And here again, if success rate is high, it's either a good or a bad news for us, depending on our goal in this research. So there's an example. You're still a lemonade manufacturer, and you change an ingredient in the recipe of your lemonade. So this likely makes the drink taste a bit more acidic, which is undesirable. The 2AFC test helps checking whether the lemonade made with the new recipe is significantly perceived as more acid. So 30 panelists are asked to taste two lemonades, former and new recipe, and panelists do not know which one is which. And panelists might identify which lemonade tastes more acidic. Once again, we're going to set up the experimental design, and second step, we'll launch the experiment and analyze results. So this time we'll be using the 2AFC test type. Go back to XLSTAT, design of sensory discrimination tests. I will select 2AFC here. And I want to check to select my own labels. So they are right here. These are the labels for the former recipe and the new recipe. So I named them X and Y so that the assessors or the panelists don't really know which one is which. I select them like this, and I get my experimental design. So product number 1, which is the former recipe, is X. Product number 2, which is the new recipe, is Y. In this case, in 2AFC, as you can see, each judge receives 2 samples, only 2 samples, X and Y. Now we know that the correct answer anyway is Y. So it's Y, which is supposed to be hypothetically more acid than X. Then each assessor gives her or his answer. So, and we get here the summary of the successes and failures. So once we get all the data, we can launch the analysis. I'll go to sensory data analysis and sensory discrimination tests once again. So this time the test type is the 2AFC test. I will be choosing the other model just to show you how it works. So I will choose the Thurstonian model. This model computes a specific statistic, which is called G prime. G prime is a number which measures the difference in perceived intensity between the two products. So here I'll select the resulting data, which are right here. Okay. And I click OK. So here I get this D prime value right here. So D prime is always positive. And when it's close to 0, it means that the perceived distance and intensity between the two products is quite low. So in this case, we must be happy. The distance in perceived acidity between the two recipes is low. Now, some of you may ask me, what is a threshold of D prime which is too high? I wouldn't know how to answer this question. It really depends on the traditions in the different industries. But anyway, if you want to know a bit more about the thresholds, you can check this article here, which will give you a few clues. So now that we've compared two products, let us switch to another method, which will allow us to map the distances between several products. We'll be using projective mapping and mapping and analyzing the data using STATIS. So we want to map the differences among 10 French wines. 11 panelists are asked to taste them and place them on a sheet. And you obtain, thus, 11 X and Y coordinate configurations. So this is how the data looks like. In rows, we have the different wines. And in columns, we have the configuration for each panelist. So this is the configuration for judge number 1, the coordinates of the different wines for judge number 1, number 2, number 3. And so on until 11. So STATIS will generate a synthetic map of the distances between products after erasing or eliminating the distortions which are linked to each specific judge, as I showed you earlier in this webinar. And one of the benefits of STATIS is that it limits the influence of atypical judges. You have other methods such as GPA, which is available in XLSTAT also, which can also be used for this kind of data, but does not really eliminate the influence or limit the influence of atypical judges. STATIS is good for this. In the STATIS jargon, the configuration corresponds to a block of input variables. In our case, each judge will produce a configuration of 2 variables. So each judge will be a configuration of X and Y coordinates. So let me configure a status analysis in XLSTAT. So here are the data. So I will run sensory data analysis and STATIS. Here I need to select the different configurations. So X1 to 11 to Y11. I need to specify to XLSTAT the number of configurations. We have 11 different configurations, 11 different panelists. The number of variables per panelist is equal. So we have only two variables per panelist, and it's the same so for all panelists. Otherwise, you can have a user-defined number of variables you can introduce here. You can add configuration labels. This means the judge or panelist IDs. I don't have panelist IDs here, so I will just skip this one. And I will just include object labels, so wines here, and click OK. So I obtain a mapping, which is right here, and which I will comment right here. So we have a mapping of the different products. The interpretation here must be similar to the interpretation of a PCA for those of you who are familiar with principal component analysis. So first of all, we need to check the amount of information from the distances among products, which is summarized on this map. In this case, we have almost 70% of the information from the distances, which is summarized. And you need to be very careful to only interpret the products which are far away from the 0, 0 coordinate here, from the central coordinate. So the products which are too close to the center do not really have a characteristic profile, at least on this map here. So what can we say here? We see that we have three different clusters of similar wines. For instance, we have these two, we have these three, and we have these two. So we have three specific groups of similar wines. We have one which is a bit atypical here, and two which we cannot really characterize. Okay, so this is how we draw a mapping using STATIS and we interpret it. Then STATIS provides many other outcomes or outputs. For instance, it tells you how much every judge or configuration was adjusted in order to have a synthetic map. We see that, for instance, configuration number 10 or judge number 10 had a very different way of arranging the products on the sheet. So it was very, very corrected. It was very distorted compared to the other judges. So STATIS really made an effort to limit the distortion of this judge. So let us just check in the data what this judge looks like. If I go on mapping, this is judge number 10. Look, obviously, this judge didn't use the X coordinate on the sheet and only aligned or arranged the products vertically, so on the Y axis of the sheet. It's quite funny. Okay, so now that we've measured the global distances between two products first with discrimination tests and then between several products with mapping, we'll switch to another method, which is sensory product characterization, which will help us see which specific attributes characterize this product compared to another one. So what is sensory product characterization? We can ask what sensory attributes best characterize each of the products, and this method would help us answering this question. The data we use are data from descriptive experiments, which we also call sensory profiling experiments. And the statistical techniques behind are based on analysis of variance, which we also call ANOVA. This is a modeling technique that allows for means comparisons. What will happen is one ANOVA will be computed per sensory attribute. And the factors in this ANOVA which are involved are the judge effect, the product effect, and optionally session effect and interaction effect. So we'll be able to say out of this analysis, such a product is characterized by a strong aroma of chocolate and a weak taste of milk. This is the kind of specific information we'll be able to extract. So you should know before running the analysis, there's a feature in XLSTAT which is called DOE for sensory data analysis, which allows to design a descriptive experiment. So let me just show you quickly how it works. So DOE for sensory data analysis, there it is. Imagine you have 8 products to compare, and you have 15 assessors in your panel, and each assessor is only able to test 4 products. This is some kind of a technical constraint. You can add several sessions. Say you will run a test today and you run a test next week. Okay, so this is a very important constraint that will drive the randomization of the experiment in order to ensure the best usability of statistical methods afterwards. You can add assessor labels also if you want. If you have any assessor IDs or names, you can add them here. So I click OK, and I get my experiment, which is right under here. So see, in session 1, you have one first session here and the second one here. In session 1, you have 4 rows per assessor, and each assessor will test 4 products. So assessor number 1 will test products 1, 2, 3, 4 in this order. Assessor number 2 will test these 4 products also in this sequence, and so on. And here you simply need to add all the sensory attributes you want to test. For instance, I don't know, saltiness, acidity, and stuff like that. So you just fill out the information right here on a Likert scale or on other scales. Okay, this is the data we'll be working on. So the chocolate data I told you about earlier. Okay, so I will launch a product characterization on these data. There it is. Here in Y, I will select all the descriptors or the sensory attributes. The products, I select them here, assessors or panelists, and sessions. Okay, quite straightforward. In the options tab, you will see that there are many possible ANOVA models to include. I will choose the simplest one, this one. So attributes equals product effect plus judge effect plus session effect. So in other cases, you may be interested in including an interaction between product and judge. But in this case, you are assuming that there could be a lack of agreement between your judges, which means your panel is not specifically well trained for this kind of exercises. But if you really trust your panel, you can go for the simplest model here. Okay, so there will be one ANOVA per attribute. I click OK to see the results. So I will just be focusing on one of the most interesting parts of the analysis. So first, here you have the discriminating power by descriptor, to what extent each descriptor is well discriminated across products. Check the p-values here. If the p-values are really low, it means that the descriptor is significantly discriminated across products. So you have a big table here, which is summarized in these charts. Okay, each chart shows the difference compared to the average of each attribute and for each product. So here, as you can see, you have chocolate number 1. In blue, you have the significant positive differences for the attributes compared to the average. So product has a score significantly higher than average for the attribute under consideration. So chocolate 1 has a significant higher score of cocoa aroma, cocoa flavor, acidity, bitterness, and astringency compared to the average. Whereas in red, you have the negative effects. So chocolate number 1 has a milk aroma score, milk flavor, caramel, vanilla, and sweetness score, which are significantly lower than the average. And you can say the same, can have the same kind of interpretations for chocolate 2 and chocolate 3. So in this way, you are really characterizing each chocolate for each specific attribute. Then product characterization also provides you with PCA analysis, which maps the different attributes with the different chocolates. So I will sum up evaluating differences between products. Difference experiments allow evaluating distances between products without getting into the details of sensory characterization, whereas descriptive experiments provide a thorough description of sensory attributes of different products, as we've just seen with product characterization. Among the difference experiments, we saw discrimination tests that help evaluating the difference in perception between only two products. We saw the triangle test and two AFC tests. We also saw projective mapping experiment, which helps mapping sensory distances between several products. We're not constraining ourselves only with two products. Here we are mapping several products. We use STATIS data analysis in this case. And at last, we saw sensory product characterization, which is based on descriptive experiments and helps characterizing a series of products over several attributes. So this one provides a more detailed characterization of the products. And it's based on ANOVA models. Now, what if we introduce an idea of affective testing in the analysis? This will be the topic of the upcoming webinar taking place on September 17th, so the day after tomorrow. Don't hesitate to register if you haven't done so yet. I will take a few questions for saying goodbye. And is it possible to do the analysis when discrimination test was done using repetition? So yes, if you're designing a discrimination test in XLSTAT, you can definitely generate several sessions. So 2 sessions with 30 panelists. Okay. You get one first session with the 30 panelists and a second session with the 30 panelists. Okay. What happens is, if your power is low, should you redo a test? Well, if your power is low and you have a significant difference, you are very lucky because you were able to detect the difference, with the p-value, even though you had a lack of power. So in this case, you just don't do anything, you have your conclusion. Otherwise, to increase your power, you can either redo the test, while including many more panelists, or you can also try to rely on another approach, which is the Thurstonian approach. That would be my suggestion. Should you ever consider removing outlier judges? So do you remember here in STATIS, we saw that judge number 10 had a very specific way to arrange the objects on the map, but this doesn't necessarily mean that he's or she or he is a bad taster or not non-experimented judge. The thing that you should be checking instead is maybe this chart. This chart measures the RV coefficient between each configuration or each judge and the consensus. So the lower this coefficient, the more the judge is far away from the consensus. Check out judge number 6 here. This is, to my opinion, a judge who is an outlier because he's really far away from the consensus. So in this case, maybe judge number 6 should be checked out again to see if she or he should be removed from the analysis. I hope you enjoyed this webinar. I hope we'll be able to talk together again on Thursday. And don't hesitate to, if you want to go further in your analysis, to ask for consultancy or to ask for specific trainings that are really tailored to your needs with the XLSTAT team. Okay, thank you very much. And I wish you a good day or a good evening according to where you are in the world. And talk to you on Thursday. Bye-bye.